Recall that we studied two varieties of exponential functions. We examined both increasing exponential functions and decreasing exponential functions. Now, both of these exponential functions can be used to model uninhibited exponential growth or decay. What does that mean? Well, when a quantity, such as a population, investment, radioactive substance, E. coli bacteria, something, grows or decays at a rate proportional to its size without any inhibiting factors, the quantity can be modeled with an exponential function. Generally, these models follow the same formula. Let's look at the details of that formula. The amount of a quantity A that grows at a rate, K, proportional to its current size over time, T, is given by the model A of T equals A naught e to the kt, where A naught is the initial amount of that quantity. So A naught is the amount that you begin with. If you're modeling an investment, it's your initial principal. If you're modeling a population, it's your initial population. Relating this to the graph, it's going to connect to our y-intercept. So at time 0, the population or investment would be A naught. Now, do notice here our independent variable is t. So we could go ahead and label our horizontal axis t. Our vertical axis is going to give us the amount of the substance, population, dollars, whatever. Same thing will be true for a decreasing exponential curve. So that initial amount is always associated with that y-intercept. Now, k gives us the rate of growth. So if k is positive, we have an increasing population. If we have a negative rate, we have a decreasing population. Also notice that our exponential model is based on the natural base e. So anything that grows relative to that natural base can be modeled with this formula. Let's take a look at a specific example of when this formula would apply. On example 5, we'll be discussing wildlife management. At Wild West Wildlife Rehabilitation Center in Amarillo, Texas, Education Director Lisa Talley, who is my very own sister, uses dermestid beetles. Now, what is a dermestid beetle? It is a flesh-eating beetle. Sounds like the stuff of nightmares, right? She uses these beetles to clean skulls of deceased wildlife so that the skulls can be used in education programs. So you see a picture over here of her Virginia opossum. After its fate, she used dermestid beetles to clean the flesh, including the skin and the gums, and they did a great job on the skull, left behind this pristine skull of the opossum that she can use to then educate the community. Now, if Lisa started with only 10 adult beetles and had 30 adult beetles after 40 days, how long would it take for the beetle population at WWWRC to grow to 10,000 beetles, assuming uninhibited exponential growth? So we're going to model this with our exponential model, A of t equals A naught e to the kt, where the A represents the amount of the beetles and t is time. So our independent variable is time. That's going to be measured in days. And A is the population in number of beetles. Now, just in case you're wondering where these beetles come from, she actually orders these things in the mail. So she'll get flesh-eating beetles, or sometimes she'll have worms to feed her reptiles. You want to be careful when you're at her house when there's a box on her doorstep. You never know what's going to be inside. So let's look at this model. She's going to start with 10 beetles. Now, the start of the experiment means time 0. So at time 0, she has 10 beetles to begin with. So 10 is the initial amount. We can use that to update our model here. In place of A naught, we'll put our initial 10 beetles, but we still have some unknown information in our model. Remember, t is the variable, but k represents a constant. That's going to be the rate of growth. So we want to know how fast is this beetle population growing. Well, we have a little bit of a clue. We know that after 40 days, the population grows to 30 adult beetles. So time is 40, population is 30. So we can solve for this rate of growth by plugging in 30 beetles for the population, and we can plug in 40 for time. That's 40 days. So we can begin solving for k by dividing both sides by 10. We want to isolate that exponential expression in order to solve. So we have 3 equals e, and I'm going to rewrite that 40k. Notice we have an exponential equation for which we cannot get like bases. So there's no common base between 3 and e, our natural base with the approximate value of 2.718. So to solve this equation, we're going to convert it into logarithmic form. Recall, when we have base e, we use a natural logarithm. So we're going to write this as natural log, which is base e, of 3 equals exponent 40k. Now, to solve for k, I just need to divide both sides by 40. So it looks like our rate of growth, k, is equal to natural log of 3 divided by 40. So once again, we can come back to our model and update it a little bit. Now we know the rate of growth. So our exponential model now is a of t equals initial population 10 beetles, base e, our rate of growth is natural log of 3 divided by 40, and we have our independent variable t, which is time and days. Once we have this model developed, then we can use it to predict future value. So the next question is how long, that is how many days, would it take for the beetle population at WWWRC to grow to 10,000 beetles? So we want to know, what is the time value when our population is 10,000 beetles? So we'll plug in 10,000 for our population, and then we have an exponential equation that we can solve for t. So to begin solving for t, we'll divide both sides by 10. That gives us 1,000 equals e to the natural log of 3 divided by 40 times t. Again, we have an exponential equation for which we cannot obtain like bases. So we're going to convert it to logarithmic form. Because we have base e, again, we're going to use a natural logarithm. That's automatically base e. So we have natural log of 1,000 equals the exponent, natural log of 3 divided by 40 times t. So our goal now is to isolate t. Notice t is multiplied by the fraction natural log of 3 divided by 40. So I'm going to multiply both sides of this equation by the reciprocal of that fraction to isolate t. So I'm going to multiply the right side by 40 over natural log of 3, and the left side by the same fraction, 40 over natural log of 3. So that is going to cancel the coefficient of t on the right side, and I'm going to switch it around. Let's put t on the left. We'll have 40 times natural log of 1,000 divided by natural log of 3. So that's our exact solution, by the way. So after that many days, she will have 10,000 beetles. But let's go ahead and approximate this with our calculator. So we want to evaluate 40 natural log of 1,000 divided by natural log of 3. And that's going to give us, to the nearest day, approximately 251 days. T is approximately 251 days. So to be formal, we can say after about 251 days, Lisa can expect the beetle population to grow to 10,000 beetles. My sister is absolutely amazing in the work that she does with wildlife, but I want to say The stuff of my nightmares is flesh-eating beetles, but the stuff of her nightmares is natural logarithms. The good Lord certainly gifts everyone differently, so we all need each other. Okay, I love that example. Let's look at another one that's quite interesting that is based on an exponential model. Radioactive half-life. Radioactive iodine-131 is a byproduct of a certain nuclear reactor. So iodine-131 is an isotope. I just want to point that out because we've studied asymptotes, and sometimes those words get confused. So we're looking at an isotope of iodine. On April 26, 1986, one of the nuclear reactors in Chernobyl, Ukraine, experienced a massive release of radioactive iodine. Fortunately, iodine-131 has a very short half-life of 8 days. If the original amount of iodine-131 released by the Chernobyl explosion was 100 grams, how much would be left after 5 days? Round to 2 decimal places. All right, radioactive substances decay exponentially. So they are an example of an exponentially decreasing quantity. For that reason, we can model it with our model A of T equals A naught e to the kt. Now recall, A naught is the initial amount of the substance that we're working with. So notice in the problem it says original amount, that's at time 0. The amount of the substance was 100 grams. So our independent variable is T. Our dependent variable is A. T is going to be measured in days. A is going to be measured in grams. So at the beginning of the problem, at T equals 0, we had 100 grams. Remember that initial amount is what we call A naught in our model. So we can go ahead and update our model. A of T equals 100 e to the kt. Remaining in our model is K, the rate of decay for this radioactive substance. So in order to have a complete model, we need to know what that rate is. And we're going to be able to figure out what that rate is using the information about the half-life in this problem. It says the half-life is 8 days. What that means is whatever amount of the substance we begin with, after 8 days, we're going to have exactly half of the original amount. So we could say after 8 days, there would be 50 grams left in the atmosphere. So I'm going to plug 50 in for the amount, and we'll plug 8 in for T. So to solve for K, we're going to divide both sides by 100. On the left side, notice we get 1/2. That's where the half-life comes from. And let's call that 8K. To solve for K, we need to convert to exponential form. So we'll rewrite this natural log of 1/2 equals 8K. And then we can solve for K by dividing both sides by 8. So it looks like our rate of decay, K, is equal to natural log of 1/2 divided by 8. Now, if you type this into the calculator just to approximate it, I want you to notice that it gives us a negative value. Natural log of 1/2 divided by 8 is a negative number. So we are dealing with a rate of decay. But now that we know that rate of decay, we can go back and update our model again. So now we can say A of T equals initial amount 100 e to the k. Now our k is natural log of 1/2 divided by 8 times t. Once again, once you have a complete model, then you can use it to make predictions. So the next question is, how much would be left after 5 days? So we want to know after 5 days, how many grams of the substance would be left behind? We can simply calculate A of 5. So we'll plug 5 in for T. And we'll just use our calculator to approximate this. And we're going to round to 2 decimal places. Now, before we jump to the calculator, remember we have a decaying substance. So if we started out with 100 grams, After 5 days, we should anticipate having less than 100 grams. So let's see if that comes out on our calculator. So we'll type in 100, second E, to natural log of 1/2 divided by 8 times 5. And we certainly get less than 100 grams. Now, another way that you can type that in, if you want to see the fraction, is to use your alpha y equals there. So you can see the natural log of 1/2 in the top and your 8 in the bottom times 5, if that's easier to see. So to 2 decimal places, we end up with 64.84 grams. So A of 5 is approximately equal to 64.84 grams. We can officially say after 5 days, there were 64.84 grams of iodine 131 in the atmosphere. It's interesting that the wildlife model and the radioactive decay model are exactly the same. They both follow that natural phenomenon of exponential growth and decay. Another thing that seems unrelated to wildlife population and radioactive decay is financial investment. So let's look at another application of these exponential functions: compound and continuous interest. Accounts which earn interest periodically throughout the year are called compound interest investments. Now recall, a simple interest investment is one in which you receive interest once per year. So a compound interest investment, you receive interest multiple times per year. Did you know that there's another type of interest? That is, some investments pay interest continuously throughout the year. That requires a completely different formula. So a periodic compound interest investment follows a formula that looks something like this: A equals P times 1 plus R over N exponent NT. So if you earn interest multiple times per year, the amount in the account can be calculated with this formula. So let's make sure we understand what all of those variables represent. A is the accumulated amount in the account. So how much will be in my account over time? P is the principal, or the initial investment. How much money do you begin with? R is the rate of interest. Most of the time that's quoted as a percent, but in the formula we're going to calculate with that percent in decimal form. So make sure to convert the percent to a decimal when using that formula. N is going to be the number of times interest is compounded, which is a fancy word for paid, per year. So if you're looking at simple interest, you're getting interest one time per year, N would be 1. Whereas if you're looking at quarterly interest, you're going to get interest 4 times per year. And then finally, T is going to be time, and this is always measured in years. So if you're looking at a 3-year investment, T would be 3. If you're looking at a 6-month investment, T would be 1/2 or half of a year. So that's the compound interest formula. Continuous interest is a little bit different. The idea of continuous interest is that you're continually earning interest at every possible instant in time. With a little bit of calculus, we could show that our periodic compound interest formula translates into what I like to call the PERT formula, A equals PE to the RT. So A, P, R, and T have the same representation of the variables in the compound interest formula, but notice this is now an exponential function with that natural base E. What I want you to notice about this continuous interest formula is that it's really similar to the models we were just looking at. The question is, how is the continuous interest formula similar to the general exponential growth model? Well, remember, our growth model was A of T equals A naught e to the kt. So in this case, A naught, the initial amount, is now represented as P. P is the initial amount of our investment. And the K, which we said was the rate of growth, is now the rate of interest, R. But fundamentally, the models are the same. As far as using the periodic compound interest formula, you want to be aware of a little bit of terminology. We want to be able to determine the value of N if the interest is compounded quarterly. Now, quarterly means you're earning interest 4 times per year. Monthly means you're earning interest 12 times per year. So we're looking at the value of N in each case. Weekly earnings would be 52 times per year. Daily earnings would be 365 times per year, although you got to read the fine print. Some banks use 360 days per year. Again, you just have to read the specific policy of the bank. If you earn interest annually, that means 1 time per year. Semi-annually means 2 times per year. So in that case, N would be 2. With that in mind, let's look at a couple of examples. Example 7 deals with savings. Suppose you want to open a compound interest savings account. Notice we're dealing with compound interest, not continuous interest, with an initial deposit of $100. Bank A advertises an interest rate of 3.9% compounded quarterly, and Bank B advertises 3.5% compounded monthly. Which is the better investment? So again, we want to recognize we're looking at compound interest. So our formula is A equals P times 1 plus R over N exponent NT. And we're beginning with $100. That's our initial deposit, so that's our principal. So we can update our model and replace the principal with our initial investment, $100. Now, we have 2 possibilities. We have Bank A advertising a rate at 3.9% compounded quarterly. So at Bank A, we have 3.9%. Remember, when we type that in for our rate, we're going to do so in decimal form. So we're going to move the decimal 2 places to the left. So we'd use 0.039 for the rate. And we're looking at quarterly compounding. This means N is going to be 4 times per year. Contrasting this with Bank B, the details are a little bit different. We're still starting with $100. But Bank B advertises 3.5% compounded monthly. So the rate at Bank B would be 0.035 as a decimal. And we're looking at monthly compounding, so N is going to be 12. So if I'm a customer trying to choose which bank, Bank A is more attractive because the rate is higher, but Bank B is more attractive because I get interest 12 times per year as opposed to 4. So we want to know at the end of the year which is going to be the better investment. So let's take a look at Bank A, and again, here is our plan. How much will we have at the end of 1 year at Bank A? So we'll calculate the amount in our account as 100 times 1 plus the rate, which we're going to use 0.039. We're going to use 4 for N, and in the exponent we have 4 times T, and we're looking at a 1-year investment. So let's see how much we would have at the end of 1 year. I'm going to assume more than $100 because our money should be growing. So let's type it in. 4 times 1 on the exponent. And we end up with, to the nearest penny, $103.96. So we have 103.96. So at the end of the year, we've earned $3.96 in interest. Okay, let's type in the values for Bank B. So the future amount, the accumulated value, is 100 times 1 plus, this time our rate is 0.035. We're looking at compounding 12 times per year and for 1 year. So typing in our details, we have 100 times 1 plus 0.035 divided by 12 raised to the 12 times 1. So in this case, we have $103.56. So our accumulated value, 103.56. Now, it's not too big of a difference when we start with an initial amount of $100, but if we had a larger principal, then there would be a bigger difference. But in our case, it looks like Bank A will be the better choice. Bank A is the better investment. At the end of the year, you earn just a little bit more interest. Okay, last question on investments. How long would it take an investment to double at 7% continuous interest? Notice we're not getting interest compounded multiple times per year. We're looking at continuous interest. So in that case, we're going to use that PERT formula. A equals PE to the RT. How long would it take an investment to double at 7% continuous interest? So all we know here is 7% is the rate. So our rate is going to be 0.07 in decimal form. How long means what is t? So I'm trying to figure out the t value, but I don't know the principal or the future value. All that we know is that however much we invest, it's going to double. So if I start with $100 for P, I could use $200 for A. If I start with $1 for P, I would anticipate $2 for A. But if you want to keep it general, you can say if you start with P dollars, you're going to end up with 2P dollars, right? And we have e to the r, which is 0.07 times t. Notice what happens if we model it this way. If I divide both sides by p, the p cancels on both sides. So we end up with 2 equals e to the 0.07t. This is an exponential equation for which we cannot get like bases, so we convert to logarithmic form. So we have natural log of 2 equals 0.07t. Then to solve for t, we're going to divide both sides by 0.07. And our exact value is natural log of 2 divided by 0.07. And by the way, the general way to calculate a doubling time is natural log of 2 divided by your rate in decimal form. That will work for any possible investment. Okay, so we have natural log of 2 divided by 0.07. So remember, t is always time in years. And we're looking at about 9.9 years. This problem didn't tell us where to round, so we can say expect the investment to double after about 9.9 years. So financial investments, radioactive decay, even wildlife population growth are all based on the same model.